Okay, in this section we're going to talk about the cross product. We've talked about two different ways to multiply vectors. You could take a real number and multiply it by a vector, and that's just called scalar multiplication. All that does is make the vector longer or shorter. It changes the magnitude, it doesn't change the direction. And then the last time we talked about the dot product. That has some important applications. When you take a dot product of two vectors, you get a number. That's really important. And if the dot product is 0, that means the vectors are orthogonal. Okay? Anyway, so today we're going to talk about what's called the cross product of two vectors, and it's very different from the dot product. One major difference is when you take a cross product of two vectors, you get a vector. Okay, it turns out it's a vector that's orthogonal to both the vectors A and B. Okay, well, we'll get to that in just a second. Before we talk about cross products, we need to talk about what are called determinants. A determinant, this is a 2 by 2 determinant. It's just an abbreviation for this expression that comes up a lot in math. If you haven't seen this expression come up, keep taking math classes because you will. The product of A1B2 minus A2B1 can be represented by this determinant. Notice it would be this product minus this product, okay? So then a 3 by 3 determinant, A1, A2, A3, B1, B2, B3, and C1, C2, C3 is written like this. This is how you can keep it straight. It's going to be A1 times the 2 by 2 determinant you have when you take out the column and row of A1, okay? So you take this out and this out. What you're left with is B2, B3, C2, C3. Now the tricky part in this definition is this minus sign. That's built into the definition, so don't forget to put that there. Minus A2 times the 2 by 2 determinant you have when you take out the column and row of A2. So you get B1, B3, C1, C3. And then it's plus A3 times the 2 by 2 determinant when you take out the column and row of A3, B1, B2, C1, C2. So here's how we define the cross product of two vectors. A cross product of vector A cross with vector B is the 3 by 3 determinant where the first row would be ijk. Remember, those are vectors. And in the second column, I should say that the first row, the second row, you put the components of the A vector here and the components of the B vector there. The order is really important because A cross with B is not equal to B cross with A. Anyway, how do you compute it? Well, what you do is you would take, for example, if this is A and this is B and you want to find the cross product, you would write it like this first. ijk, the components of A are right here, the components of B are right here. And then you could reduce that to 2 by 2 determinants. Remember, it's the I vector times the 2 by 2 determinant 1, negative 2, 0, 2, minus the j vector times the determinant that's left when you take out the column and row of j. So you get 2, negative 2 times negative 1, 2 here, determinant, plus the k vector times the 2 by 2 determinant 2, 1, negative 1, 0. So then when you finish this off, it's the I vector times the product 1 times 2 minus 2 times 0, so you just get 2 minus 0, minus the j vector, don't forget there's a minus sign here, minus the j vector times 4 minus 2 I should say, 4 minus positive 2, that's right, plus the k vector times 0 minus negative 1, which is just 1. So this is what you get when you get the cross product. Notice it's a vector. It's a vector because in the determinant, the first row are vectors. So that's why it turns out to be a vector. Okay. This theorem here is important. It gives a geometric interpretation of the cross product. Notice it's not saying the cross product equals this. It's the magnitude of the cross product, right? The magnitude of A cross B is the magnitude of A, magnitude of B sine theta, where theta is the angle that's between them. So one thing you notice right off the bat is under what circumstances is this 0? This is 0. The magnitude of the cross product is 0, or let's just say the cross product is the 0 vector. If either A or B are 0, okay, or the sine of theta is 0. The sine of theta is 0 and theta equals 0 or pi, right? That means that A and B would have to be parallel vectors. Now it turns out we define the 0 vector to be parallel to every vector, so you can actually say this. The only time a cross product is the 0 vector is if A and B are parallel. It's kind of like what we talked about with dot products. With dot products, it looks similar. This was A dot B, and this was a cosine. If the dot product of two vectors is 0, remember they're orthogonal or perpendicular. But if the cross product is the 0 vector, that means the vectors have to be parallel. In fact, this is really important. Probably one of the most important things. You can actually show this, that if you look at the cross product of A cross with B, it's going to be orthogonal to A and B. The way you show it's orthogonal to A is just take a look at the dot product of A cross B with A, and you'll show that that's 0. It's easy to see. And then you take the dot product of A cross B with B, and that's 0 too. So the dot this with A, you get 0. Dot this with B, you get 0. That means that it's orthogonal to both. So it turns out this will be a vector that's orthogonal to both. Now you use what's called the right-hand rule, kind of like what you used. They call this a right-handed coordinate system. If you're crossing A with B, suppose this is A and this is B over here, then using your right hand, if A cross with B, the vector will go, A cross B will be in the direction of your thumb. But if A is over here and B is over here, when you look at A cross B with your right hand, your thumb is going to be going down. Okay, so what that actually shows is that A cross with B is -1 times B cross with A. We'll talk about that in just a second. Let me do some more of that. Okay, when you cross I with J, okay, I'm using the right hand rule, going from I to J with my right hand. I can't see that very well. There you go. Notice I dotted with J is going to be perpendicular to I and J, and it's going to go up, isn't it? So that would be the K vector. But by the way, if you cross J with I with your right hand, you can't really see this very well, can you? Going from J to I, you can't see that at all. Your thumb is going to be going down. So actually, J cross with I is going to be -K. All right, J cross with K is I. J cross with K. Here's J. Here's K. And so when you cross them, you get I vector. And then K cross with I. K cross with I, you get J. K with I, J. It's going that way. Anyway, so get good at that. I did mention there are these properties of cross products in the book. You can look at those, but this is a big one. When you take a cross product, I have this backwards. It should say A cross with B is -1 times B, or the cross product of B with A. That's what it should say. Okay, when you cross A with B, it's -1 times the cross product of B with A. So if you were to commute the two vectors, you pick up a net negative sign. Anyway, there's some other important properties as well. So on your homework and in future sections, you might have to find this. Find two unit vectors that are orthogonal to these two vectors. Whenever you hear the phrase, find a vector orthogonal to two vectors, you should think immediately cross product. So we're going to form the cross product of these two vectors. And then we're going to turn that cross product into a unit vector, okay? So you're going to cross A with B, so you get ijk, 1, 0, -2, -1, 2, 1, and then you can write it like this. And when you form when you actually finish this, you would get the I vector times 0 plus 4 minus the J vector times 1 minus 2 plus the K vector times 2 minus 0. So this is your cross product. This is the vector that's orthogonal to both A and B. Now how do you form it, turn it into a unit vector? You take the magnitude of that cross product, you get the square root of 16 plus 1 plus 4, which is the square root of 21. So when you divide both of all the components by the square root of 21, you've turned the cross product into a unit vector. There's two of them. There's one that's going to be going up, there's one that's going to be going down. I'm not sure which is going up and which is going down. I have to look at these vectors, but this is one vector that's orthogonal, one unit vector that's orthogonal, and this is another one to be the opposite of U. Okay, let's do a little bit more here. This is going to come up in the next section. I want to find a vector that's orthogonal to this plane that contains these 3 points. So 3 points, as long as they're not collinear, they determine a plane. If you think about this picture here, suppose I have these points P, Q, and R, point P, point Q, and point R. I can certainly form these 2 vectors, PQ. PQ would be this vector. PR would be this vector, right? And I can put them next to each other. And these 2 vectors lie in this plane. And if you take the cross product, I can form this vector n. This vector n would be orthogonal. It would be orthogonal to this plane. What does that mean? It means it's orthogonal to every vector in the plane. How do you form this vector? You would first of all, you would form the vector PQ. You'd take the difference in the x coordinates. 1 minus 1 is 0. 0 minus negative 1 is 1. 2 minus 0 is 2. And you'd also form the vector PR. 2 minus 1 is 1. 1 minus negative 1 is 2. 0 minus 0 is 0. And then you would cross PQ with PR. And when you do that, you get this, I times this determinant minus j times this determinant plus k times this determinant. And then when you finish this process, you get I times 0 minus 4 minus j times 0 minus 2 plus k times 0 minus 1. So this is the vector that will serve as what's called the normal vector, or the vector that's orthogonal to every vector in this plane. Pretty cool, huh? One last thing I want to mention. This is kind of nice. We're talking about an application of force was the idea of work. Remember, I meant to say an application of dot product back in section 10.3 was the work. The work done when you apply a force to move an object a distance d. The work done, as I showed last time, is the dot product of the vector f with the position vector d. All right. Well, torque is kind of an interesting application of cross products. Suppose you have a wheel that's spinning, okay? Now it's spinning in the counterclockwise sense, okay? So if you're looking on top of it, it's spinning this way. So I'm applying a force that tends to move this wheel in the counterclockwise sense. So this is the center of the wheel. This is the position vector r. If I were to move this force vector so that it's in a parallel fashion, so it's over here and it's touching r, what is r cross f going from r to f? Do you see, is it going to go up or down? Is my cross product here going to be up or down if I take r cross f? Well, you should have gotten down. It's a vector that goes like this. This is the t vector. This is r cross with f. It's going to be going down. It's going to be orthogonal to f. Orthogonal to r. It's going to be going down because of the right-hand rule going down. Your right hand should be pointed down. You can't see that. So the more the force, it turns out the greater the force that's moving this wheel, the longer this vector is, the magnitude is that's going down. Okay. Now, if in fact you were applying a force that was causing a counterclockwise spin going this way, so you'd be applying a force maybe tangent to the wheel this direction. If you were to move that force vector in a parallel fashion over here next to r, can you see that r cross f? If you take the cross product of r and f, now going from r to f, you can see that the vector is going to be going up. So for this kind of spin here, the cross product would be this vector sticking up like this. It's going to be orthogonal to r, orthogonal to f. It's going to be going up because of the right-hand rule. Interesting, huh? All right, we'll see you next time. Bye-bye.